This video is about the force that a charged particle experiences as it moves through a magnetic field. And when we ask ourselves what the governing equation for force is, the answer is what it's always been in physics. Sigma F equals ma. Your job whenever you're talking about a magnetic force like this is to draw a free body diagram, determine what goes into sigma F, and then start solving it like it's any other force problem. Obviously, I don't have a free body diagram here. You don't know what I'm talking about. But I hope you can tease out of this that the only force the particle I'm looking at experiences is a magnetic force. And apparently it's moving in a circle because I've put in the equation for centripetal acceleration. After that, you just need an expression for what the magnetic force is. The magnetic force's expression is here. It's the charge on a particle times how fast it's moving times the strength of the magnetic field. There's clearly some direction dependence here because we have this trig expression which seems to suggest that the angle affects the strength of the force as well. So on a fundamental level, magnetic forces are no big deal. They act like many other forces. There's also a key difference, and the key difference has to do with direction. In this video, I'm going to attempt to go through and explain some of the nuances of the direction of magnetic forces. In a subsequent video, we're going to talk about how we can use this direction for practical applications. This device is going to help us figure out the direction of the force on a charged particle moving through a magnetic field. The charged particle in question is an electron. They get produced at this plate, and all this stuff at the bottom has a positive charge, so that makes the electrons fly down towards the bottom. Now we can't look at an individual electron. That would be really hard to do. There's a gazillion of them being made every second. But this device lets us see what would happen to the path of a single electron. Let's look at how. All of this stuff at the bottom has an important shape. The bottom plate has a big slit through it, and the screen here, which is coated in a phosphor, so when electrons hit it, it glows, is at an angle. So we don't really see a single electron, but electrons that are farthest from me, like here, they only get to go through the slit, and they only go a short distance before they hit the screen. Electrons at the other end of the disk go a long way before they hit the screen. So that lets us see at the top of the screen we have electrons that only went a short distance. At the bottom they went a long distance. If there's a curve, we'll know that there's a force, and the electrons up here only have it for a short time. Here they have it for a while as they travel down the screen. So it'll kind of give us an idea of the path electrons are taking. So I have to show you what I mean, so I'm going to turn it on. All right, so there's our beam of electrons. You can see it's more or less going down. So now I've got a magnetic field, which is going to be caused by a bar magnet. Now we've studied this magnetic field. We know that it leaves the north and goes over to the south. But we also know that this is three-dimensional. So this is happening in front of the magnet, below the magnet, and behind the magnet. It's going straight away from the north, curving around, and going into the south. Just to remind you, we looked at this, and this shows what the field looks like in 3 dimensions, symmetrical. So what I'm going to do is I'm going to bring my north pole towards that beam of electrons. And the magnetic field out of the north pole is going to be straight away from the camera. And we're going to see what happens to those electrons. I want you to predict what direction they're going to move in. It pretty clearly moves to the left. Let's try to figure out why. So I don't know if you were surprised by that, but it was very interesting the directions that the beam of electrons moved. If you think about it, if I have a magnetic field inwards, we could say that's along the x-axis. The beam of electrons is moving down like this. So we could say that's along the y-axis. But what was the direction of the force? The direction of force was left. So that's along, we could say, the z-axis. So this was a truly three-dimensional situation. We had an electron moving down with an inward magnetic field, and that caused a force to the left. So that's one of the cool things about magnetic forces. They involve all three dimensions. Let's see what happens if we bring a south pole towards the screen in exactly the same fashion. As you can see, the beam of electrons moves to the right. So I want to talk about this idea that we use all three axes. We use something called the right-hand rule in order to make this happen. It turns out that we have up and down, we have left and right, and we know those are two independent dimensions. But there's a relationship between the positive direction in the up-down dimension and the positive direction in the left-right dimension. I have to show you what I mean. I don't know if you've ever seen these signs before. They're in Waterford, Connecticut, and at first glance they're nothing remarkable, two highway signs. But when you look at them for a little while, you realize that east and north shouldn't be like that. It's almost like one of them's pointing in the wrong direction. And that's a really remarkable statement, because if we think of east as being on the x-axis and north as being on the y-axis, we've spent so much time in this class saying x and y are independent. But it turns out that's not really true. There is a relationship between them. And here's what I mean by that. When we assign direction, we use this compass. And north to the right of it is supposed to be east. So if we assume the 156 sign is right, and east is straight ahead, to the right of us should be south, not north. Now, Route 213's excuse is that it does a U-turn. It's kind of a U-shaped road. But the point of all this is we're not completely free to ignore the directions that dimensions have relative to each other. That's going to be incredibly important as we deal with magnetic force, which operates in all three dimensions. So we see that in nature there is a relationship between different dimensions. So the way you remember this when it comes to magnetic forces is use something called the right-hand rule. If you take your finger and you go like this, you actually can make a little x, y, and z axis. And your index finger corresponds to V. Your other fingers correspond to B. Your thumb corresponds to F. Let's look at that a little bit closer. So here's a closer look. And as you can see with my hand, the three things are pointing in all three dimensions, x, y, and z. And basically they're pointing in the positive direction in each axis. The way you remember it is essentially that it's written as F equals QVB. And F is your thumb. And then you look at the other side of the equation. Q is not a vector. It doesn't have direction. V is your first vector, so it's your top finger. And then B is your second vector, so it's your other fingers. Takes a little practice to remember, but this always gets you the right directions, just like we know how north should be related to east. So the idea that you're having mutually perpendicular forces is actually really weird. And just to demonstrate how weird this is, I want to pretend that I am a charged particle. I'm such a positive person, I'm going to make myself positive. And I'm going to run with a certain velocity. And we're going to figure out what kind of force we have on me using the right-hand rule. So, make my axes. I'm pointing my index finger in the direction I'm moving. And I'm turning my wrist until my other fingers are pointing in the direction of the magnetic field. And my thumb is pointing into the board. So the force on me would be into the board. It's hard to draw an arrow like that. This picture here kind of helps us. If we're looking at an archery arrow from the side, it's got a tip and some feathers. If you're looking at it straight on, if it was coming at you, you kind of see the tip of it. If you're looking at it from the back, you'd see the feathers as it moved away from you. So we use this symbol for something going away from you, this is something going towards you. And the right-hand rule says that this force is going away from me, into the board. So let's act that out. If this white thing is the chalkboard, I'm going to start at the other end, and I'm going to run with this velocity. And me being a positive charge, I should experience a force this way, which is down. What would that look like? All right, here I go. I got sucked into the floor by the magnetic force, and it hurt. What would be much more fun is if I go this way. And again, we still have to apply the right-hand rule. Let's do it. V is like that. Magnetic field is that way. I should be experiencing an upward force here. A magnetic force like that. Coming out of the board, which in real life corresponds to up. So what would that look like? Let's give it a try. The right-hand rule applies to positive charges moving through a magnetic field. Notice we had negative charges, these electrons. So whatever the right-hand rule tells us about the direction of force, we should expect the opposite. Your index finger, you point it in the direction that the charges were moving. Your other fingers, you curl in the direction of the magnetic field. So this is for the first one when the North Pole approached. We have an inward field, downward charges, and now your thumb is pointing in the direction of force. It pretty clearly moves to the left. And that's opposite what we saw because this is for a positive particle and we use negative particles. So a positive particle would have a force right, our particles had a force left.